Okay, so areas of regular polygons. Couple review of the words, or a review of a couple words. Regular means all sides and angles congruent. Okay, so we are talking only about regular polygons. If you have polygons that have all different side lengths, this is not the way to find the area. Okay, this formula only works for regular polygons. So that means we could talk about triangles all the way up to an n-sided figure. Okay, any number of sides, as long as it's regular, this formula would work. Okay. So triangle, if we're talking about that, I know it seems a little weird because you're probably thinking, oh, we already have a formula for triangle. And yes, in every instance where you can use the formula for the triangle as a whole, I would do that. And I'm going to show you one instance where the book would want you to use the polygon formula, and I'm going to suggest you use the regular formula.
What is that N-G-O-N mean?
N-gon means an n-sided figure. Not a nonagon. A nonagon is a 9-sided figure. An n-gon could have n sides. N could be 4, it could be 8, it could be 100. Okay. All right, so you do need to know what regular means. There's a couple other vocabulary words that come in that you probably have not dealt with. Well, one of them you have, but not in this context. So the first thing you're going to do is draw a hexagon. Make it as regular as you can. If it's not perfect, that's okay. But we want to be able to draw a circle around it so I can explain one of these vocab words. Not bad? Okay. Once you have that, find the center of that figure. Okay. We are going to draw from the center to a vertex. We're going to draw a line. Now, if we're talking about that line in the circle, what would you call that?
The radius.
The radius. That's exactly what we're going to continue to call this. Okay, so because that vertex, or each of these vertices touches the circle, or should, from the center to a vertex is a radius. It's a radius of our polygon as well. So a radius of a polygon is a line from the center to a vertex. Okay, could be any vertex of that shape. The next thing we're going to talk about, from that center, you're going to drop a perpendicular line, perpendicular to the side. So we're going to bring this down so we have the side and that line are perpendicular. And this is a vocab word you probably have not dealt with yet. It is called the apothem. Apothem. It's got the poth, but that's okay. That poth in it, but that's about it. All right, so the apothem, and the radius could be anywhere in this figure from the center to any vertex. The apothem could be drawn from the center to any side. So don't get confused if it's not straight down. I could draw a radius and I could draw an apothem here and a radius there. Okay. So the apothem is the line from the center perpendicular to a side. The reason you need to know these vocab words is if there is no picture and the instructions tell you what the length of the apothem is or what the radius is or what a side is, you need to know which dimension they're giving you, what piece. All right, now the first thing we need to establish before we actually get into the formula itself is finding angle measures. Because in the event that we don't have a dimension that we need, we're going to have to use special right triangles, or you could use trig. We're not going to in this case, but you have those options if you know some angle measures. So we're going to stick with the hexagon for the purpose of showing you how to find angle measures. So we're going to do another hexagon. Since these are all regular figures, that means every single side is congruent. And since every single radius is congruent, because that's the nice thing about being in a circle like it is up here, is wherever you draw a radius, it's going to be congruent. In order to fit it into the polygon, they have to be to a vertex. But that means every single one of these is congruent as well. And the reason we're discussing that is because that means every single triangle is congruent. Okay? That's why we can only do this with a regular figure. Now, the side lengths, or the name of the figure, you're going to want to pay attention to because that tells us how many of these triangles are in here. If it's a hexagon, it has 6 sides and therefore 6 triangles. Okay. What we're going to start out with is finding the measure of these 6 interior angles. Now, back up to the circle a minute. Since this is inside of a circle, what would you expect that these should add up to?
360.
360. So that makes it easy because once we have that one point that they share, we know that every one of these congruent angles adds up to 360. So since there are 6 of them, 360 divided by 6 makes each one of them 60 degrees. Okay. So we're going to leave this one a second because we're going to do more with that. But each of these, for a hexagon, would be 60. If I were to draw in that apothem, okay, so we're going to add that one into just one triangle. What do you suppose happens between these 2 angles? A bisection. That's a perpendicular bisector. So each of these would be congruent, making those 30, right? And you might see where this is going. Some of you have already thought about it, I'm sure. Since this is 30 and this is 90, that makes both of these 60. Okay? And if you're thinking ahead, if I have a 30, 60, 90 for a hexagon, if I'm missing any pieces that I'm going to need, I can use the special right triangle ratio to find them. Okay? So that's where knowing the angles comes into play. If they weren't a 30 or a 60 or a 45, if you didn't get one of the special angles, knowing the angles, you could still find the angles. They just might not be one of the special right triangles. Just to show you, that is where you'd use trig instead. Okay, but we're not going to do that in this case. So you might want to make a note in case you look back at these. Your central angles add up to 360 degrees. Okay.